Grade 10s, welcome to our 9th lesson. Today we are looking at the center of mass. Center of mass. This is your teacher, Marshall A.C. Candiado. Right, so in the previous lesson, remember we looked at the concepts of turning effect, right? Turning effect, we saw how when you have children sitting on a seesaw, that's the best example that just came to my mind. Kids sitting on a seesaw, how they're able to balance each other out because of what we call clockwise moments and anti-clockwise moments, right? I hope you guys do remember that. We saw how there is what we call turning effect of a force, wherever you are turning an object about a fixed point, such as a pivot, right, a fulcrum, and we gave examples of, what is the thing called, a spanner? Yeah, a spanner, and someone is turning, nuts and bolts and stuff, right? So we gave reference to moments in that lesson, right? And how you had the weight of the individual multiplied by the distance from the pivot, and it gave you the moment. Okay. So today now we are looking at the center of mass. The center of mass, what I'm going to do generally in this lesson is just give you a general overview. I'm not going to read these notes. These notes are for you to read. They're not for me. I can't be going around reading notes at this stage in my life. So you guys, by the end of this lesson, you should be able to define the term center of mass, and you should be able to describe the implications of an object's center of mass in relation to its stability. We're going to do that in this lesson, and we are going to do that also in lesson 10. Okay? So just compose yourself, and that's what we're going to be doing in this lesson. So you can just pause the video, look at the just two of them, just two objectives, and just amuse yourself on those. Okay, so why I gave the example of the kids sitting on the seesaw was that when they are balanced, right, when you have Rita sitting that side and you have Devin sitting that side, and let's assume that they have the same mass. I don't know, maybe one of them is heavier, maybe one of them is lighter, I don't know. But given that they have set in, even if they have different weights, right, we found that if they sit at certain positions on that seesaw, they will be able to have an equilibrium. Now, the center of mass, where I'm trying to go with this, is that there is a position on every object. There is a position on every object where if you were to handle it, right, if you were to hold it at that position, the anti-clockwise moments would be equal to the clockwise moments. And by just holding the object at that exact point, you would not even feel, say, the weight of the object. It would just be easy if it was a chair or if it was a desk, and you find the exact center of mass of that object. You would just be able even to lift it with the finger. If you've ever watched those gymnasts, do you know gymnastics? Those guys who do gymnastics, and then they're able to lift an individual, and the individual just seems like they're so light, as if they're lifting just a paper. Hope you've watched. You know the thing with the internet, just Google gymnastics and just Google those aerobics guys. You'll see how they do it. But that's the concept that they actually make use of. They find the individual center of mass, and by holding them at that position, the person effectively doesn't weigh that much. So when we have an object, let's think of, let's look at, I had an image here, right? So let's look at this image. This person is holding, this is a stick with two balls at his hands. I'm assuming one ball is heavier than the other ball. That's why his hand or his finger is not in the middle, right? You can see that it's slightly towards the right. So what this individual has done is that where he is holding or where she is holding, because from that hand we can tell if it's a boy or a girl, a man or a woman. Right. So where that person is holding is effectively the geometrical center of that object, if the object is regular. Right. That is the geometrical center of that object. Right. So by holding or by placing his or her finger at that exact point, that object then is balanced out because that object, he or she is holding it at its center of mass. Then we also have this idea that the center of mass is also known as the center of gravity. You might be asked to say, so what then is the difference? Why call it the center of mass? Why not just call it the center of gravity or either way? When we are on this planet, I haven't paused at any point, but because it's simple stuff, to me it seems like it's simple. If you want, you can just pause the video for a minute or two, just have a read up on all these things that are on the screen, and I can just continue after you've just read those things. Right, so I was saying, I hope you paused the video. I was saying that in relation to center of mass as compared to center of gravity, there is this idea that center of mass can actually be different from center of gravity. When does this happen? This can only happen, like right now we are all sitting on the Earth's surface. It doesn't matter where you are, whether you're in Walvish Bay, whether you're in Oshakati, whether you're in Tsumeb, whether you're here in Omalala. It's irrelevant where you are. We are all on the Earth's surface, and therefore the same force of gravity is acting on us, right? It's acting on us irrespective of altitude. Therefore, our center of gravities and our centers of mass are effectively at the same position. The gravity is the same at all these different places. We denote it as 9.8 meters per second squared. That's the force or the gravitational pull. So all the objects that are here, if they are all on the ground, then their center of mass and center of gravity is the same. However, if you were to have an extremely big object, that maybe goes, let's say, 100 kilometers into the sky, because that object is going so high up into the sky, its center of mass, just imagine a big rectangular block or a huge building, right, that goes all the way into the sky. Its center of mass and its center of gravity are going to be different because gravity actually reduces as you go up into the sky. So the higher you go, the gravity actually reduces bit by bit. So if you're at the top of maybe, let's say, a very high mountain, I wonder which high mountains you guys have here in Namibia. You will tell me in tomorrow's lesson. But if, let's say, you're on top of Kilimanjaro, right? Tallest point, highest point on the continent. Or you're on top of Everest, highest point in the world. The gravity on top of those mountains is different from the gravity that we have here on the surface, right? So the center of gravity for that extremely huge object is then going to differ from the center of mass. You will replay this, you will read out, you will Google until you get to understand what it is that I am saying. Okay, so now if we have now knowledge of this center of mass, we say, okay, so if I have an object and we say that this object has a center of mass, what are the implications? Why are we talking about these positions of the center of mass? So now observe how the center of mass is critical in determining the stability of a body. The stability, right? You will find that with higher or taller, the higher the center of mass, the less stable an object is. I'll just give simple generalization. The higher the center of mass, the more easily an object can be toppled over, the less stable it is, right? So we give this example of how when you have tall people are less stable than short people. Short people, because they are closer to the ground and because they are shorter, they actually have a lower center of mass, which makes them more stable. If you've ever seen boxers always assume almost like a crouching position, because either they're already short, but if they're tall, they almost bend their knees because they're trying to lower their center of mass and therefore increase their stability. So if we have Tuna and we have, who is tall in the class? Veta or Tino? It's not Tino, obviously. I think it's Devin or Veremue, right? If we have Devin and we have Tuna, right? Or if we have Veremue and we have Tuna, then, or Vicky and Veremue, we know that Vicky is going to be more stable because she's shorter. She's shorter, therefore her center of mass is lower. Her center of mass is lower, therefore she is more stable, right? So when you look here, we have examples: sports cars, F1 cars, and these are double-decker and triple-decker buses. We don't have those here. It's just that most of the information that we get it from the Cambridge books, and they're from London, right? So these are triple-decker buses, double-decker buses, and you will find that because of how high they go, they are not that stable because they are very high, right? I also had an image here, which I know this is just a guy who is walking on a tightrope. I hope you can see this. I hope you guys can see this guy. Yeah, he's walking on a rope. He's in the air. He's not walking on the ground. And if you are familiar with your wall structures, I'm sure you can tell that that's the Eiffel Tower. And if you know that's the Eiffel Tower, then you know which country that is in, right? Let me just do this. Okay, so what we have on the screen right now, this is an image of a double-decker bus, and it's being tested for its stability, right? They're not just going to make these big buses and then just put them in the road at the risk of people, this thing just toppling over and then harming people. So what they're doing here is that, let me just go here, where it says, I hope this thing is clear for you guys to see. Yeah, cool, there. The stability of a double-decker bus is being tested in figure 11.6b. We just saw the image. When the top deck is fully laden with passengers, and they are simulating this by putting sandbags. It must not topple if tilted through an angle of 28 degrees. So what they are doing in this image, let me just pause. So what they are doing here on this diagram is that they have tilted the bus to an angle of 28 degrees as a simulation to say, okay, so if we were to tilt this bus, or if something was to happen and it was to tilt at an angle of 28 degrees, would the bus topple over? And if it doesn't topple in this simulation, they also realize that, okay, so if it's on the road and people are on the bus and it's full at the top, because realize that if it's full at the top, its center of mass again also rises, which makes it even less stable. But when there's people both on the first floor and then also on the top floor, then first deck, top deck, then it's more stable because of that, right? So that's just testing the stability to see if the object will topple over or not. So if we look at the low center of mass, bodies with the low center of mass are the most stable. They are the most stable, and they cannot be toppled over easily. We'll find that with these ones, we say that they can be toppled over easily, right? Cars with a high center of mass or gravity can easily turn over, and they are not safe to drive at a high speed. So these buses, you wouldn't expect to drive them at a high speed. But these cars now, the F1 cars, racing cars, Lamborghinis, cars like those ones, with a very low center of mass, right? With a very low center of mass, they can be driven at extremely high speeds, 200, maybe 250 Ks I think Lewis Hamilton sometimes clocks 300 and something Ks. That's how fast they can go because of how low their center of gravity is and how stable they are, which means they're extremely safe. You can't do the same thing when you're driving a car that doesn't have that sort of balance. Short people are more stable than the than the tall ones. That's what I was saying earlier. The shorter people are more stable, right? And the taller people are more likely to fall than the shorter people. It's a fact. It's not one of those, no, me, I've never fallen. I'm also just a bit tall. But if someone is shorter than me, then they are more stable, right? Yeah, and they're saying that when you sit down, right, when you sit down or you crouch or you increase the space between your feet, you spread your feet, and then you give yourself a wider base. You increase your stability. These are some examples of how you reduce the stability. You see, by overloading vehicles reduces their stability because now you have increased and you have raised the center of mass. Just look at this. Just look at these different situations, right? So when this is a Peugeot. These Peugeots are from long ago. You we've never seen cars like this, but I'm sure you've seen overloading. This is extreme. Are those people? Are those things? Are those bags? What is that? Right? So the center of mass is now very high, and because the center of mass is very high in all of these images, these cars, if they were just to turn at a very, maybe even at 15 degree angle, just if one of the wheels goes off the ground, they are probably going to topple over. So what I want you guys to do is I want you guys to just read over this material and just get a basic understanding of what center of mass is. Right? In the next lesson, we'll also look again at the effects of the center of mass, and we'll look at how we can determine the center of mass using a lamina and on different objects. So I would like to thank you guys for watching the video. I'll be asking you the different examples I gave in the video. If you are hearing me say this, it means you already watched the video, so you're good. I will ask you these things in tomorrow's lesson. Okay? Remind me if I don't ask. Say, sir, you said you ask us certain things from the video. Please ask us now. Okay, so thank you guys. This is your teacher, as always, Marshall A.C. Kanyadi.